horizon that we're seeing is not physical. It's
No,
refracted.
nothing.
Correct?
Nothing. You right. Hold your hand out in front of you. Is that your physical hand you're seeing?
Correct.
No, it's not.
A reification fallacy is when you treat a model or a mathematical construct as real. We are not doing that.
So an actual scientific model
Yeah.
explains natural phenomena, as you said. So,
Yeah.
but it can only be considered as a scientific model if it can be objectively tested by experimentation. So what have you got to experiment on for your globe model?
All the measurements that back up what the globe model says, and the fact that it's able to make accurate predictions and cohesively explain everything that's going on.
Well, we'll start with the prediction. What is a scientific prediction? In all cases of science, as the scientific prediction is the hypothesis. Do you agree?
No, the prediction isn't the hypothesis. You use the hypothesis to make a prediction.
From ThoughtCo, the hypothesis. It states the purpose of your experiment, the variables used, and the predicted outcome of your experiment. From verywellminded.com, a hypothesis is a tentative statement about the relationship between two or more variables. It is a specific, testable prediction about what you expect to happen in a study. Also, the hypothesis is a prediction, but it involves more than a guess. The hypothesis is absolutely a scientific prediction.
So that's what a scientific prediction is: a hypothesis with an independent variable and a dependent variable.
Again,
what would you
they're
say
not. They're
then?
not. They're not the same thing. You get your hypothesis, which has your IV and your DV, and you use that hypothesis to make a prediction about future events. The hypothesis isn't the prediction. They are different things.
But what about from geosociety.org? The hypothesis should contain a prediction about its verifiability.
But do you know where the scientific model sits in the scientific method? Where do we get the scientific model from?
The scientific model comes from the collection of information that we have. All the explanations, all the experiments, all the equations, everything that all match up that are able to make the phenomenon. The model comes after you've got lots of different data that you can put together.
The scientific model is the result from experimentation and it's been validated by experiment.
So, yeah, you do understand that it's not a physical thing. It's a collection of experiments and explanations and everything.
Just so there's no confusion, the explanation of a natural phenomenon, i.e. model or theory, must be testable by experimentation. In other words, once a model is proposed as an explanation of a phenomenon, it can only be considered scientific model if it can be objectively tested by experiment.
So obviously you've got a globe model. So it's been put through experimentation. What sort of experimentation, what natural phenomena has led you to this globe model?
What? So you want me to, for instance, apply rotation of the Earth along the scientific method steps? I mean,
Sure.
For me, my natural phenomenon, my natural observations would have been the sky that I saw when I was in the Royal Navy, looking at the way the sky acts as I move away from the North Pole towards the equator. For me, that suggested that we would be on a spherical surface. So my observation was the way that the stars behave in the sky, and my hypothesis from that would have been that the Earth is in fact rotating. You can have a dependent variable of the position of the stars, an independent variable of your position on the Earth, to actually make that basic observation, and you can make some predictions based on that. So if the Earth is rotating at the 15 degrees per hour that my hypothesis would suggest, then
sorry,
yeah.
I don't mean to interrupt, but you kind of got two things going on. You got rotation of the sky and rotation of the Earth. Which one is the natural phenomenon?
Well, my observation was the way that the stars move, and my hypothesis
do you want to stick with that?
Yeah, but my hypothesis from that was that we are on a spherical object that's rotating.
So to have the dependent variable, you have to have one effect, one dependent variable. What are we picking? The rotation of the sky or rotation of the Earth?
My dependent variable will be the position of the stars in the sky. That's something that can be measured,
the
right?
Position or the rotation?
Well,
what are you observing?
Again, your prediction is separate from the hypothesis, right? Based on my observation of the way the stars are moving when I'm traveling throughout the world, I have the hypothesis that we are on a rotating sphere, all right? My hypothesis for that would be the dependent variable would be the position of the stars in the sky, which would be the thing that you measured, and the independent variable on the Earth, which would be something that I could manipulate. So that's my hypothesis, is that we're on a rotating spheroid because of what I see in the sky. So then I need to make a prediction based on that hypothesis. So I've got my hypothesis that we're on something that is a sphere that rotates at 15 degrees per hour. Now I make a prediction. And my prediction would be something as simple as performing the Foucault's pendulum experiment at different positions on Earth and predicting the outcome of that based on the fact that we are rotating at 15 degrees per hour. And I can then do those experiments, see if I get the predicted amount of drift based on the Coriolis effect, and then see if that matches the prediction that I made based on my hypothesis. The thing is, your hypothesis doesn't have to directly relate to what your experiment is.
The hypothesis doesn't have to directly relate to what your experiment is, or the scientific method begs to differ. From geosociety.org, once a hypothesis has been established, it is time to test it. Also, an experiment is designed to prove or disprove the hypothesis.
Hang on, that's what you're testing though. The hypothesis is the experiment, is in the experiment. You're testing the hypothesis in the experiment.
No, you're not directly testing the hypothesis.
What about from sciencing.com? The scientific method involves asking a question, doing research, forming a hypothesis, and testing the hypothesis via experiment. And if you still don't like that, from ThoughtCo, it is important to note that a hypothesis must be testable. That means you should be able to test your hypothesis through experimentation. And then in the experiment, once you've developed a hypothesis, you must design and conduct an experiment that will test it. Is this guy completely scientifically illiterate?
And so if that prediction is the hypothesis is an educated guess.
So does that contain the independent and dependent variable in the hypothesis, or is that in the experiment?
Well, they both have them. You have your IV and DV for a hypothesis, and your experiment has an IV, a DV, a CV.
Exactly. So you are testing the hypothesis in your experiment.
No, the IV and the DV in the hypothesis will not be the IV and the DV that are in the test, in the experiments. They're different things.
This is just getting embarrassing. From geosociety.org, the hypothesis should contain a prediction about its verifiability. For example, if the hypothesis is true, then 1 should happen when 2 is manipulated. 1, the dependent variable, depends on what you're doing. In 2, the independent variable. You manipulate it to get a reaction. And here's the kicker. There should be no other variables in the experiment that may affect the dependent variable. That means you've only got one dependent variable and one independent variable in your experiment and your hypothesis. And once again, under the experiment, once the hypothesis has been established, it is time to test it. Oh, this must be painful to watch for the Globers. From ThoughtCo, only testable hypotheses can be used to conceive and perform an experiment using the scientific method. Only testable hypothesis.
So what are we actually doing in the experiment? Why is the Foucault pendulum coming to this? How does the Foucault pendulum work? Is the Earth rotating under the Foucault pendulum as it swings? Is that how it's working?
Technically, yes. It's got a fixed pivot point, and the fact that the bob is moving, you can make a prediction as to what the drift would be if the Earth is rotating at 15 degrees per hour.
And so what happens when I launch my drone from this rotating Earth and the drone doesn't drift at 15 degrees per hour as the pendulum does?
The pendulum won't drift at 15 degrees.
You just said the pendulum. What do you mean? What's drifting at 15 degrees per hour? Is it the
entire Earth? No, the entire Earth is rotating at 15 degrees per hour. A pendulum won't. Well, a pendulum would rotate at 15 degrees per hour. A pendulum won't drift at 15 degrees per hour.
Well, a pendulum would rotate at 15 degrees per hour. A pendulum won't drift at 15 degrees per hour.
Your motivation of your actual experiment, though, like what are you actually testing in your experiment to get to the globe model?
I'm testing my prediction. If the Earth is rotating at 15 degrees per hour, then physics says
it's not the Earth. It's to get to. Sorry,
that's my hypothesis. That's my hypothesis. My hypothesis is that the Earth, the thing I am standing on, is rotating at 15 degrees per hour, which is the reason for the stars moving the way they are. That was my observation and my hypothesis from that. So then I've made the prediction.
Sorry, let's go from the top. So we've got an observation of stars rotating.
No, not rotating necessarily, just the way that the stars acted in the sky as I traveled throughout the world. And the measurements that I took.
So all you're changing by moving location is what you're seeing in the sky. You're not actually manipulating what you think is rotating, whether it be
you don't have to actually manipulate what you think rotates. You have to change something in the to give your cause and effect relationship. And based on the fact no, it's really not.
Yeah, you really do have to manipulate the independent variable. From the Office of Research Integrity, the change that we create as a result from a manipulation. Also, therefore, in experiments, a researcher manipulates an independent variable to determine if it causes a change in the dependent variable. The pain's still not over. From LibGuides, the independent variable, it refers to the condition of an experiment that is systematically manipulated by the investigator. It is the presumed cause. And just in case you're trying to block your ears, from Boston College, notice that the manipulation of an independent variable must involve the active intervention of the researcher.
So if I was to say to you, we've got the hypothesis of Earth rotating at 15 degrees per hour, what would you say could be a prediction for that?
A prediction? Well, I say the prediction is the hypothesis. You've got the independent and dependent variable. So you observe something.
They're different things. Prediction and hypothesis are different things. You have to separate them.
Nope, they're one and the same. From Thorco again, hypothesis. It is the statement used to predict the outcome of an experiment. From verywellminded.com, it is a specific, testable prediction about what you expect to happen in a study. Also, the hypothesis is a prediction, but involves more than just a guess. So stop asserting otherwise, Globe Zealots. A scientific prediction is the hypothesis. They are one and the same.
So how is it that you come to the conclusion using this experiment that you're on a rotating globe? What is it what differentiates the sky rotating to the Earth rotating? How can you prove
because
that
my prediction would be nothing to do with the sky. Would be the dependent variable would be the position of the stars in the sky, which would be the thing that you measured, and the independent variable would be my position on the Earth, which would be something that I could manipulate. My prediction would be nothing to do with the sky. You're mixing up. There's no way the sky moving would make a pendulum drift. Yeah, but my hypothesis is that the Earth's rotating, so I'm going to make a prediction based on that, right? So I'm making a prediction.
Only changed your location. So
yeah, I can change
location, you're not manipulating anything that's moving. You're just changing.
I'm manipulating a part of one of the variables in the experiment that would change the measure of the thing that you've measured. So, in this case, my position on the Earth, which is why I'm able to use the prediction of, based on your latitude, your pendulum will drift a different amount.
That's a presupposition on the globe.
No, it's not
from Polaris.
We all know what a latitude is. They're the lines of latitude that are agreed upon by everybody. If the Earth is a globe, which has those lines of latitude, right? We're making a prediction here, and the globe has lines of latitude, so we're using that as part of the prediction. If the Earth is rotating at 15 degrees per hour, physics says that a swinging pendulum will induce a drift a different amount depending on the latitude it is.
The only problem is you're not actually manipulating anything. You're changing.
I'm manipulating my position.
That's not an independent variable. You're not.
Yeah, absolutely
manipulating anything.
I've manipulated the position I've done the experiment in.
We're definitely not.
I could also manipulate the time. I could make the independent variable the amount of time that the bob swings for. In experiments, time is usually an independent variable.
Not an independent variable. No, time would be the cause for absolutely everything. If it was
not if that wasn't the thing that you were manipulating. You decide what the independent variable is.
You're not manipulating the course of time. All you can do is
you're manipulating the amount of time in the experiment. Yeah, exactly. So you've manipulated the time.
You can't go.
It absolutely is.
It absolutely
forward. It absolutely is changing the time in the experiment. You manipulate something in the experiment, in this case, the amount of time. That is what you manipulate to change the measured phenomenon, which would be the dV.
All right, so we're not.
I'm sorry,
we're
but
kind of
you
going
are
around
you are
circles
you are
with
out. You're completely wrong that time can't be an independent variable. And maths is very, very important, because maths is actually how you make your model, and maths is how in science you prove your ideas.
Incorrect. Maths can't prove anything. Maths
No,
is
math.
not
It's
something
not
that's
incorrect.
in reality.
Maths is literally the only way that you prove things. Science doesn't prove things. Maths does prove. Maths is where you find proofs. This isn't something that's up for discussion. This is a fact. Maths is how you prove your ideas in science, according to science.
What's the empirical method, the empirical model here? Is it science or is it maths?
Science is
proves
how you
things
prove your
empirically?
ideas.
So you can prove things with science.
No, you prove your ideas with maths. Science gives you the explanations and the experimentation and the method of doing things. You prove things with maths.
Alright, enough stuttering through your doublespeak. From Geosociety. An experiment is designed to prove or disprove the hypothesis. From ThoughtCo, write the hypothesis in such a way that you can prove or disprove it. Another one from Geosociety. Science is often more about proving a scientific statement wrong rather than right. How embarrassing, a flat earther proving the scientific illiteracy of a globe zealot. Just another kick while you're down. A testable hypothesis is a hypothesis that can be proved or disproved as a result of testing.
And this is just a fact of science that
Maths
really,
is a description, it's a language. So that can
and it's
come
how you
after,
prove
and
your
you can
ideas
use
in
maths
science.
through experimentation, through testing your hypothesis, or what you say, your prediction. So you've got the independent and dependent variable, and you're verifying, you're validating that prediction, aren't you?
Yeah, and
that's how
you prove your ideas with the math behind it.
A reification fallacy is when you treat a model or a mathematical construct as real. We are not doing that.
Because the science gives you
It's just a
evidence for
description.
something. Yeah, the science gives you evidence for things, and you prove that ideas, the evidence and everything, by describing it with maths. You know, that's
What
literally
kind of
how it
evidence
works.
you get? You don't get mathematical evidence, you get scientific evidence.
Yeah, and then you describe that evidence using mathematics. This is how
Correct,
you do
describe
scientific
it, but
papers.
that's not the
Yeah,
proof.
and that's what the proof is. The proof is the descriptive element of it using mathematics. That's literally what proof is. Because science does not prove things, maths does.
It's almost unfair at this point. From Lumen Learning, you must be able to test your hypothesis, and it must be possible to prove your hypothesis true or false. And from Genome, students are taught the proper way to do science is through the following steps. First, devise a hypothesis, and then design experiments that will prove or disprove their theory. And down the bottom, it seems obvious that this is the appropriate way of moving forward in science. In fact, in most published papers, the hypothesis is put forth, followed by experimental proof. This is not up for discussion, Globers. Science absolutely proves things, and mathematics proves nothing. It's just reification.
So do you want to use this as kind of the scientific method here? So we've got an observed natural phenomenon. So we're observing something in the sky, and what would you say in the hypothesis or your prediction, whatever you want to call it, what would you say is the independent variable?
But we're not. This isn't a scientific experiment or a hypothesis we're doing.
This
is a prediction.
No,
this is a prediction that came from the model. So
you absolutely have to observe something first. So if we're observing an eclipse, you propose the cause to the eclipse. Now, what's the cause to the eclipse?
Well, it would be the moon going in front of the sun.
Okay, and how can we manipulate that?
By changing the position that would be on Earth, and that would change the actual amount that the moon would be covering the sun.
Yeah, I see why you went with positions, because that's not actually manipulating. You can't go backwards.
It absolutely is. It doesn't matter. That's not what manipulating means. Manipulating just means changing the variable. It doesn't mean physically going and touching it. Don't be.
What a surprise, the scientific method disagrees. From sciencing.com, the independent variable is the variable the scientist is actively changing over the course of the experiment. From the Office of Research Integrity, change that we create as a result of manipulation. Also, In experiments, a researcher manipulates the independent variable to determine if it causes a change in the dependent variable. From LibGuides, it refers to the condition of experiment that is systematically manipulated by the investigator. And from Boston College, notice that the manipulation of an independent variable must involve the active intervention of the researcher. It's game over, Globers. You don't have an independent variable to manipulate because you can't manipulate time or location, so you don't have a hypothesis to test, so you don't have an experiment, and therefore you do not have a globe model.
Let's do it with other things. Let's see what the model predicts about the black swan observation, about the radius value, about terrestrial refraction.
It predicts that exactly. Our model, which includes refraction,
the black swan observation.
Yeah, the heliocentric model includes refraction and makes that prediction. Mick West actually, using the heliocentric model, showed the predictions that are available. So because refraction and the way that light bends is part of the heliocentric model, the black swan is explained perfectly and predicted by the heliocentric model.
So the black swan absolutely debunks the radius value, which you use
in
terrestrial refraction, 7/6
No, it doesn't.
R. So where are you getting the R value if you haven't got an R?
You don't need to see the horizon to get a radius. That's a very silly thing to say.
Okay, how are we getting the radius then?
Well, you can measure the divergence of plumb bobs.
Plumb bobs. Are we using the plumb bob to get a radius?
Well, you can test the divergence. It's quite easy. You do some maths.
Divergence?
Yeah.
Enlighten us.
Well, the fact that plumb bobs lean away from each other, you can use that to easily calculate your radius.
Where do they lean away from each other? So you're at two places at once and you're seeing a leaning plumb bob.
Yeah, MC Toon's actually got a good experiment that Jesse Kozlowski and the main surveyor did. But we can talk, the most famous example is that there is
a plumb bob. How can you ever see a leaning plumb bob? You're only presupposing that in a different location compared to one location,
you measure
it's going to be leaning from that second location.
You measure it.
A leaning plumb bob.
Oh, you say you can't measure it, but it's been done. You can measure
a leaning plumb bob
by reciprocal zenith angles.
So Al Bruni, when he was looking at the horizon to measure the radius, was he wrong? Then you don't need the horizon. You can't use the horizon. It's refractive.
I didn't say you can't use it, but you don't have to use it.
Why don't we use it? It's there. We don't need to build bridges.
Because it's kind of hard to. Well, you don't have to. That was just a good way to do it. It's kind of hard to do it optically like that because refraction is a thing.
So you can't see physical Earth curvature.
You can see a refracted version of it. The fact that there's a horizon is because of the curve of the Earth.
What's things disappearing bottom up from then? It's not physical Earth curvature.
It's still going over the horizon.
What's the horizon? Is it physical or is it optical?
It's a refracted part. Everything you see is refracted, but the horizon that's there,
optical.
The horizon that's there is just a refracted version of the geometric horizon, and you see things go over that just like you would expect to. Again, the refraction is part of our model. That's all explained within our model because of our understanding of light, thanks to Newton, who was the one who basically did experiments and quantification of refraction.
So it's not a physical. The horizon that we're seeing is not physical. It's refracted.
Nothing. You right. Hold your hand out in front of you. Is that your physical hand you're seeing?
Correct.
No, it's not. There's an atmosphere. There's atmosphere between your eyes and your hand. You're not seeing your physical hand. You're seeing. You don't understand how maths works. I don't. It's not your fault.
Maths. So it's nothing to do with science.
Maths, physics. Well, maths is a lot to do with science. It's the language of science and how you prove your ideas in science.
A reification fallacy is when you treat a model or a mathematical construct as real. We are not doing that.
And if you accept one part, of course I'm scientifically illiterate with my degrees in science and stuff. Of course I am. Successfully operating nuclear reactors for years. Of course I'm scientifically illiterate.
Because it defies your religion of a globe model.
I don't have a religion. I have experiments. Yeah, no, science doesn't prove things. Do you know what kind of science does prove things, Mitchell? Do you know what kind of science does prove things, Mitchell? Pseudoscience.
All science.
Are you a follower? Are you a follower of pseudoscience? Because if you're saying that science proves things, you are a follower of pseudoscience.
So now we're projecting, aren't we? So you're saying
no, not at all. You're saying that science proves things, and that isn't science. Science does not prove things. It's as simple as
The
that.
only means of knowledge at our disposal is experiment. How can we know things? How can we prove things without experiment? Math has got nothing to do if we use the scientific method to prove things. So
Scientific method doesn't prove
I'll-
things. Find me a citation that says the scientific method proves things. You won't, because it
absolutely,
doesn't.
I will.
Because he loves the pain of eating his own words, let's do it one more time. From Genome, students are taught the proper way to do science through the following steps. First, devise a hypothesis, and then design experiments that will prove or disprove their theory. It seems obvious that this is the appropriate way of moving forward in science. In fact, in most published papers, the hypothesis is put forth, followed by the experimental proof. From ThoughtCo, a testable hypothesis is a hypothesis that can be proved or disproved as a result of testing, data collection, or experience. Only testable hypotheses can be used to conceive and perform an experiment using the scientific method. From Jazz Society, science is often more about proving a scientific statement wrong rather than right. And in this video, I have thoroughly proven that the globe has no scientific backing and does not follow the scientific method. There is no globe model, and there is no globe, only flat Earth, observably, measurably, and obviously flat.
Wow.